Your kid has mastered wooden coding robots and tactile programming puzzles. They can debug a board game sequence like a pro. But now they're staring at a blank code editor, and suddenly all that confidence just evaporated. That transition from hands-on coding tools to actual typed code, it's bigger than most parents realize. I'm Dr. Priya Mehta, a child developmental psychologist who specializes in screen time impacts and tactile learning methods, and I've watched hundreds of families navigate this exact moment.
You're listening to the STEM Lab podcast. Quick note before we dive in. Everything you're about to hear, all the research, the data, the advice, that's written and verified by real human experts. But the voice you're hearing, that's AI generated. I want to be upfront about that. Now, if you've been listening for a while, thank you for being here. It genuinely makes a difference. And if you're new to the show, welcome. I think you'll find this one really useful. We release new episodes every Monday, Wednesday, and Friday, each one tackling a real question parents are dealing with when it comes to teaching STEM concepts to their kids. So here's what we're covering today.
You've watched your child master screen-free coding fundamentals through wooden robots, board games, and tactile puzzles. Now they're ready for the next step, typing actual code into a real development environment. This transition feels monumental, and it is, but it doesn't have to be overwhelming. This checklist walks you through every readiness indicator, technical requirement, and developmental milestone you need to confirm before introducing text-based programming. Whether you're moving towards Scratch's block-to-text hybrid or diving straight into Python, you'll know exactly what to prepare, what to expect, and how to support your child through this pivotal shift in their learning path. So first, let's talk about readiness indicators. Is your child actually ready? Before you install a single IDE or sign up for any platform, assess whether your child has internalized the foundational concepts that make screen-free coding to text programming transitions successful. These aren't arbitrary age gates. They're genuine developmental markers that predict confidence and competence. Sequential thinking mastery is the first one. Your child can explain multi-step processes in order without prompting, demonstrating understanding of sequence, loops, and conditionals through physical play rather than just memorizing patterns. Debugging persistence is huge. When their physical coding solution fails, the robot goes the wrong way, the board game sequence doesn't work, they systematically test each step rather than immediately asking for help or giving up. Abstract representation comfort means they can look at symbol cards, arrow tiles, or function blocks and mentally predict what will happen before executing the sequence, showing they've moved beyond purely trial and error learning. Reading fluency at grade level matters because text-based programming demands reading comprehension. If your child struggles to decode written instructions independently, they'll face dual cognitive load, learning syntax and decoding text simultaneously. Typing basic familiarity is important too. They don't need typing mastery, but they should know where letters live on a keyboard and be able to type short words without hunting for every single key. Otherwise, syntax becomes a mechanical barrier. Frustration tolerance for invisible errors is critical. Screen-free tools provide immediate physical feedback. Text programming often produces cryptic error messages. Watch how your child handles delayed or unclear feedback in other contexts. Real programming interest matters. The transition works best when driven by their curiosity about how actual apps, games, or websites work, not just parent ambition or curriculum pressure.
And comfort with screen-based learning. If you've intentionally limited screen time, as many families choosing screen-free coding have, gradually increase their comfort with focused, task-oriented screen use before adding the cognitive challenge of syntax. This isn't about checking every box perfectly. It's about recognizing where your child stands so you can scaffold appropriately. One of my daughters showed debugging persistence at 7, but needed 2 more years to develop the frustration tolerance for Python's indentation errors. That waiting period wasn't wasted. It deepened her physical coding foundations. Now, moving on to technical environment setup, getting the lab ready.
The screen-free coding to text programming bridge requires specific hardware, software, and connectivity configurations. These aren't minor details. Wrong choices create friction that undermines confidence during an already challenging transition. Let's start with hardware lab specs. For computer minimum requirements, Scratch 3.0 needs a tablet or computer running Windows 10 or later, Mac OS 10.13 or later, Chrome OS, or Android 6.0 or later with 2 GB RAM minimum. For Python with idle or Thonny, you want Windows 10 or later, Mac OS 10.11 or later, or Linux distributions with 4 GB RAM recommended for comfortable operation. Keyboard quality actually matters more than you'd think. Membrane keyboards with mushy key travel frustrate beginners who can't feel whether they've registered a keystroke. Mechanical keyboards with tactile switches provide clear physical feedback that mirrors the tactile certainty of screen-free tools. Expect to invest around $50 to $80 for entry-level mechanical options. Display size and resolution should be at least 13 inches with 1920 by 1080 resolution to prevent squinting at code editors and error messages. Younger programmers especially need comfortable visual access without eye strain during focused work sessions. For mouse versus trackpad considerations, block-based environments like Scratch demand precise dragging. External mice provide better fine motor control than trackpads for children still developing coordination, particularly those under 10. Power and portability needs depend on your setup. Laptops enable workspace flexibility, kitchen table to bedroom desk, but require consistent charging habits. Desktop setups provide stability and better ergonomics, but reduce mobility. Match this to your family's learning space realities. Next, technical environment decisions. Offline versus cloud-dependent platforms is a big choice. Scratch Desktop offers offline capability crucial for families managing screen time through airplane mode or disconnected periods, while Scratch Online requires constant internet. Python with Thonny IDE works entirely offline once installed, making it ideal for distraction-free learning.
Operating system compatibility varies. Scratch 3.0 runs on Windows, Mac OS, Chrome OS, iOS, and Android. Python runs natively on Windows, Mac OS, and Linux. Chromebook users need Linux container setup or cloud-based options like Replit, which reintroduces connectivity dependence. IDE complexity levels range widely. Thonny provides beginner-friendly Python development with built-in variable visualization and simple debugging. VS Code offers industry-standard environments, but overwhelming feature sets for newcomers. Start simple. Professional tools can wait. Account and subscription requirements are straightforward for most. Scratch requires free account creation with email verification. Many families use parent emails for children under 13 per COPPA requirements. Python itself is free and open source with no subscriptions. Cloud platforms like Replit offer free tiers but push paid plans for additional features. Version control introduction timing should wait. Git and GitHub represent professional development practices, but add cognitive overhead during initial syntax learning. Bookmark this for later. Once your child comfortably writes 50-plus line programs, version control becomes genuinely useful rather than abstractly educational. Now for connectivity and expandability path. Arduino integration timeline works especially well if your child has used physical coding robots. The Arduino IDE creates powerful continuity, programming physical devices with text-based C++. This bridge works especially well for kinesthetic learners who thrived with screen-free tools, though syntax is less forgiving than Python. Block-to-text hybrid transition tools exist. Scratch's Show Blocks and Show Code toggle doesn't exist exactly, but platforms like Blockly Games demonstrate blocks alongside JavaScript equivalents, making syntax less mysterious and connecting physical block manipulation to text representation.
Library and package ecosystem exposure in Python transforms from obstacles into opportunities, but only after basic syntax confidence. Budget 3 to 6 months in pure Python fundamentals before introducing pip and external packages. Microcontroller progression path makes sense when screen-free coding robots prepared children for physical computing. The transition path runs screen-free robots to Scratch controlling simple LEDs, to Python on Raspberry Pi, to Arduino C++, to advanced embedded systems, each step building industry-relevant skills. This technical foundation isn't optional infrastructure you can skip. It's the laboratory environment that determines whether screen-free coding to text programming feels like a natural next step or an overwhelming rupture. All right, let's get into curriculum bridge, connecting physical to digital concepts. The concepts your child mastered through screen-free coding board games and wooden robots translate directly into text syntax, but the translation isn't always obvious to them. Your role is making those connections explicit and visceral. Starting with sequence and statement translation. Physical sequence cards become code lines. When your child arranged arrow tiles in order, each tile was one instruction. In Python, each line is one instruction. Physically lay out sequence cards next to their first simple programs. Forward, forward, turn right becomes 3 lines of turtle.forward, turtle.forward, turtle.right. Start and end rituals matter. Screen-free coding tools often had clear starting positions, robot on first square, and ending states, reach the star. Programs need similar clarity. Function definitions mark beginnings, return statements mark endings. Frame these as digital versions of place your robot here. One action, one line discipline should be maintained. Screen-free coding enforced physical constraints, one action per card or block. Text programming allows cramming multiple commands onto single lines, which experienced programmers do for efficiency, but confuses beginners. Maintain the one instruction, one line rule for the first 6 months. Reading order consistency is important. Screen-free sequences read left to right or top to bottom. Code reads top to bottom exclusively. If your child used board games with directional reading variations, explicitly practice reading code only downward. This prevents directional confusion errors. Now for loop and function recognition. Repeat loops from physical stacks translate directly. The repeat 4 times tiles your child used translate to for loops and while loops. Show them. That stack of 4 identical forward cards becomes for I in range 4, turtle.forward 50. The compression from 4 physical objects to 1 text structure feels magical when you make it explicit. Function blocks as reusable sequences work the same way. If screen-free tools included create-your-own function mechanics, common in advanced board names, those become DEF statements in Python. The concept of naming a sequence and calling it later transfers perfectly, just different notation. Nested loop recognition comes from screen-free tools with loops inside loops, like repeat 3 times, go forward twice, turn right. These prepare children for indentation logic. Point out how physical nesting, placing one repeat block inside another, becomes visual indentation in Python. The structure mirrors itself. Loop exit conditions translate too. Screen-free games often had stop when you reach the goal mechanics. These become while loop conditions in text programming. Translation example, keep moving until you touch blue becomes while sensor.color is not equal to blue, robot.forward. Moving on to conditional logic mapping. If-then tiles become if statements directly. Many screen-free coding tools include conditional cards. If path is blocked, turn left. These translate directly. If obstacle detected, turn left. The punctuation and indentation are new, but the logical structure is identical. Else path introduction is something screen-free games rarely include explicitly. They imply it. Text programming makes else explicit and powerful. Demonstrate, if I laid down a turn left card for blocked paths, what did you do when paths weren't blocked? That's your else. Sensor simulation to variable checking works when your child used robots with physical sensors, color, or proximity. Those checks become variable comparisons. The Ozobot Evo color sensor checking "is this blue" becomes Python's if color equals blue. Same logic, different mechanism. Boolean logic foundations need explicit connection. Screen-free and/or gates, less common but present in advanced games, need explicit connection to Python's and/or operators. Use physical truth tables with blocks before writing Boolean expressions. This curriculum bridge phase typically spans 4 to 8 weeks of parallel learning. Keep physical tools active while introducing their text equivalents. Don't rush this transition period. The connections you build here determine whether text syntax feels like learning a new language, which is hard, or learning to write down what you already know, which is manageable. Next up, skill progression milestones, what success actually looks like. Parents often ask me when they'll know the transition is working. These concrete capability milestones mark genuine progress through screen-free coding to text programming advancement, not just time served. First month is about syntax familiarity. Your child types 3-line programs independently. They can write and run a simple sequence, 3 turtle graphics commands, 3 print statements, without asking where the parentheses go or how to indent. They read error messages aloud. Rather than freezing when red text appears, they read the message and locate the line number mentioned, even if they can't fix it yet. They identify indentation errors visually. They can look at code and spot when a line looks wrong positionally, connecting to the spatial awareness they developed with physical block alignment. They remember to save work. After losing progress once or twice, they develop the habit of saving before running code, a professional practice that mirrors putting screen-free pieces back in the box. Months 2 to 3 are about structural thinking. They write working for loops without reference. Loops are fully internalized. They know the syntax pattern and can apply it to new situations without checking examples. They plan programs on paper first. Before typing, they sketch pseudocode or draw flowcharts, demonstrating that planning happens mentally before execution, a massive cognitive leap from trial and error. They debug simple logic errors independently. When output is wrong but code runs, they identify which line produces incorrect behavior by testing sections separately. They ask specific syntax questions. Instead of "this doesn't work," they ask, "should this variable be inside or outside the loop?" showing they understand concepts but need confirmation on notation. Months 4 to 6 bring creative application. They build projects from personal interests. They propose and complete programs based on their own curiosity, a quiz game, a drawing tool, a character generator, rather than only following tutorials. They refactor repetitive code into functions. They notice when they've written similar code blocks multiple times and independently create a function to eliminate repetition, showing genuine computational thinking. They read and modify others' code. Given a working program written by someone else, they understand what it does and can change specific behaviors, the digital equivalent of remixing physical coding sequences. They connect programming to real tools. They recognize that the concepts they're learning appear in actual apps, games, and websites, positioning skills along a trajectory toward industry-standard practices rather than isolated educational exercises. These milestones align closely with what 10-year-olds can master in STEM more broadly, though individual timelines vary significantly. Some children race through month 1 milestones in 2 weeks, others need 8 weeks. Neither pace predicts long-term success. Foundational solidity matters more than speed. Now let's talk about emotional and behavioral support strategies. The technical and cognitive challenges of screen-free coding to text programming transitions matter less than the emotional ones. Syntax errors feel personal in ways that knocking over a wooden robot never did. Your child needs different support now. Starting with reframing failure feedback.
Normalize error messages as communication. In screen-free coding, wrong moves produced obvious physical failures. Text programming produces cryptic messages that feel like criticism. Frame errors as the computer asking for clarification, rather than "you did something wrong." Celebrate debugging as detective work. When your child thrived with physical tools, they could see problems. Text debugging requires inference and hypothesis testing. Position this as leveling up to more sophisticated problem solving, not confronting deficiency. Distinguish syntax from logic errors clearly. Misplaced parentheses aren't thinking mistakes, they're notation mistakes. Logic errors, wrong algorithm, reflect planning, which your child may excel at from screen-free foundations. Help them see the difference so syntax frustration doesn't undermine their confidence in their actual problem-solving ability. Use physical analogies for abstract errors. Indentation error means nothing. It's like stacking your sequence cards crooked so they don't line up, creates instant recognition. Next, managing screen time anxiety. Set clear coding session boundaries. If you've carefully limited screens, programming feels rule-breaking. Establish that 30 to 45-minute focused coding sessions are different from passive consumption. Name them building time rather than screen time. Maintain parallel physical coding. Don't abandon screen-free tools entirely during transition. Weekly board game sessions or robot challenges keep tactile problem-solving active and prevent the shift from feeling like a total replacement of valued activities. Schedule offline processing time. After screen sessions, your child needs non-screen time to mentally integrate new concepts. A 15-minute walk, building session with Legos, or outdoor play helps consolidate learning without additional visual input. Watch for eye strain and posture. Screen-free coding happened on floors, tables, with bodies moving. Text programming creates physical stillness. Teach the 20-20-20 rule. Every 20 minutes, look at something 20 feet away for 20 seconds and ensure proper seating ergonomics. Now, sustaining motivation through the valley. Acknowledge the capability plateau. Your child went from steady screen-free progress to feeling clumsy with syntax. That's normal and temporary, but they need to hear you name it as an expected transition phase, not evidence they're not good at this. Connect to their screen-free wins. Remember when the robot kept turning the wrong way and you systematically tested each card? That's exactly what we're doing with this error message. Your debugging skills didn't disappear. Introduce transitional hybrid tools if needed. If pure text feels overwhelming, platforms that show blocks and text side by side, like Blockly games, create scaffolding. These aren't retreats, they're strategic supports. Celebrate non-coding wins. When frustration peaks, point out what they are mastering. Typing speed, focus duration, reading technical documentation. Progress isn't only syntax. The research on screen time impacts and tactile learning shows that transitions from physical to digital learning environments require explicit emotional scaffolding, not just cognitive instruction. You're not just teaching Python, you're teaching resilience through a genuinely challenging skill shift. All right, let's move into platform-specific transition pathways. Different text programming environments serve different transition needs. Your choice should match your child's screen-free coding background, learning style, and where you want their skills to lead. First, Scratch 3.0, the visual text bridge.
Who it serves best? Children who thrived with highly visual screen-free tools, robots with color paths, illustrated board games, and aren't ready for pure text. Typically ages 7 to 10, or visual spatial learners of any age. Key advantage: block-based interface with drag-and-drop mechanics mirrors physical coding card manipulation, minimizing syntax barriers while introducing programming concepts through a familiar interaction model. Lab specs are straightforward, runs in browsers online or via Scratch desktop offline, works on tablets with touch interfaces, creating continuity with tactile screen-free experiences. No installation complexity for browser version. Expandability path goes from Scratch to more complex projects, games, animations, interactive stories, without changing platforms, then transitions to block-to-text languages like JavaScript through Blockly or MIT App Inventor before pure text environments. Limitation to acknowledge, Scratch doesn't prepare students for industry-standard tools. No professional developers use it. It's pedagogical infrastructure, not career preparation, which matters for families planning long-term STEM trajectories. Subscription requirements? Completely free with no paid tiers or feature restrictions. Account creation required for saving and sharing projects online. Next, Python with Thonny IDE. Direct text introduction. Who it serves best? Children comfortable with abstract thinking who showed strong reading and pattern recognition in screen-free coding, typically ages 9 and up, or those specifically interested in real programming. Key advantage: Python syntax closely resembles plain English compared to other languages. Thonny provides beginner-friendly debugging and variable visualization. This pathway leads directly toward Python for teaching AI to kids and data science. Lab specs require Python installation, free and available for Windows, Mac OS, and Linux, plus Thonny IDE installation. Runs entirely offline once installed, minimal system resources, works on older computers, no tablet support, keyboard essential. Expandability path is strong. Turtle graphics for visual output, to text-based projects, to Pygame for game development, to data science libraries like Pandas and Matplotlib, to web frameworks like Flask, to machine learning basics. Each step builds professional skills. Learning curve reality is this. First 2 weeks feel steep as students encounter syntax errors frequently. Indentation-sensitive structure frustrates children who excelled at spatial organization in screen-free tools, but struggle with invisible spaces and tabs. Subscription requirements: completely free and open source. No accounts, no subscriptions, no feature gates. This is professional-grade software with zero cost barriers. Third option, Arduino IDE, physical computing continuity.
Who it serves best? Children whose favorite screen-free tools were robots and physical devices. Kinesthetic learners who need to see code affect real-world objects to maintain engagement. Key advantage: programs control LEDs, motors, sensors, and robots, creating direct connection between screen-free robot coding and text-based embedded programming. Prepares students for robotics and IoT career paths. Lab specs: require Arduino IDE installation, free, plus Arduino board purchase. Uno starter kits run around $30 to $50. Programs upload to hardware via USB. Works offline except for library downloads. Windows, Mac OS, and Linux compatible. Expandability path is compelling. Simple LED blink programs to sensor input processing, to motor control, to multi-component systems, to custom PCB design, to professional embedded systems development. This pathway leads to electrical engineering and robotics careers. Challenge to prepare for: Arduino uses C++, which is less forgiving than Python. Syntax errors in embedded programming can damage hardware, rare but possible with incorrect pin configurations. Requires basic electronics knowledge, like circuits, voltage, current. Subscription requirements: Arduino IDE and core libraries are free and open source. Some advanced components and expansion shields add hardware costs over time. No software subscriptions. The platform you choose creates the next 12 to 24 months of your child's learning path. You can switch later, but switching costs time and creates discontinuity. Before we wrap up, let's do a final check before you go. Run through this condensed readiness verification before installing software or starting your first text programming session. Child readiness: Does your child demonstrate sequential thinking and debugging persistence with physical tools? Do they read at grade level with comprehension? Can they type simple words without hunting each key? Do they show genuine interest in real programming, not just parent-driven curriculum? Do they handle frustration and delayed feedback without shutting down? Technical setup. Does your computer meet minimum specs for your chosen platform in terms of RAM and OS version? Does your keyboard provide clear tactile feedback for keystroke confidence? Is your display size large enough to prevent squinting at code, 13 inches or more at 1920 by 1080 or higher? Is software installed and tested, runs, opens, saves files successfully? Have you established a backup and save workflow before the first real project? Curriculum Bridge. Have you identified 3 screen-free concepts to connect to first text programs? Have you prepared physical coding tools for parallel comparison during early lessons? Have you selected age-appropriate first projects like turtle graphics or simple text output? Have you set realistic timeline expectations, 6 to 12 months to comfortable competence?
Support environment. Have you clarified screen time boundaries? That coding sessions are building time? Is physical space prepared with proper ergonomics and lighting? Have you identified where to get help? Forums, documentation, parent learning? Have you scheduled regular check-ins to assess frustration and enjoyment balance? Progression planning. Have you chosen concrete milestones to track, like can-write loop independently? Have you decided whether to pursue Scratch to Python, Direct Python, or Arduino path? Do you understand what this platform prepares them for next? AI, web dev, robotics? Have you connected current learning to longer-term progressive STEM learning path? Now for some frequently asked questions. How long should we keep using screen-free coding tools after starting text programming? Continue parallel use for at least 3 months during the transition. Weekly screen-free sessions prevent text syntax frustration from undermining computational thinking confidence. Physical tools remain valuable for planning complex programs before typing them, even after your child becomes fluent with syntax. Many successful programmers sketch algorithms with paper and blocks before writing production code. The tactile problem-solving foundation you built doesn't expire when text programming begins. It becomes a thinking tool they can access when purely abstract planning feels stuck. What if my child loved screen-free coding but hates text programming after 2 weeks? 2 weeks isn't enough time to distinguish genuine incompatibility from normal adjustment friction. Most children need 4 to 6 weeks before syntax becomes familiar enough to feel manageable rather than overwhelming. First, verify you've addressed the fundamentals. Is the error message feedback overwhelming their debugging skills? Does typing mechanics create frustration separate from programming logic? Try hybrid tools like Scratch that reduce syntax barriers while maintaining programming concepts. If resistance continues past 2 months despite appropriate scaffolding, pause and return to advanced screen-free challenges. Some children need another year of abstract thinking development before text programming clicks, and that's developmentally normal, not failure. Can we skip Scratch and go straight to Python if my child is already 11 and showed strong screen-free coding skills?
Absolutely. If your child reads fluently, types comfortably, and demonstrates strong abstract thinking with screen-free tools, age 11 and up with solid foundations often benefits from skipping Scratch's block interface entirely. Python's readable syntax and direct path toward industry tools makes it ideal for older beginners who won't experience Scratch as playful discovery, but rather as an unnecessary intermediary step. Start with Thonny IDE and Turtle Graphics for visual feedback, transition to text-based projects within 4 to 6 weeks, then introduce game development or data visualization based on interests. The key predictor isn't age, but frustration tolerance for syntax errors and intrinsic motivation to learn real programming rather than needing gamified block interfaces to sustain engagement. So here are my final thoughts. The transition from screen-free coding to text programming represents one of the most significant cognitive leaps in your child's STEM learning path. You've built remarkable foundations through physical tools, computational thinking, debugging persistence, spatial reasoning, and problem decomposition skills that many programming students never develop properly. Now comes translation work. Not every concept transfers instantly, and syntax errors will test patience you didn't know you had. That's expected. The children who succeed through this transition aren't the ones who never struggle. They're the ones whose parents recognize struggle as learning in progress, rather than evidence of wrong paths. Your role shifts here from activity facilitator to emotional anchor. The technical skills will come. Your child needs you to hold confidence when error messages feel personal, to name plateaus as temporary rather than permanent, and to celebrate debugging breakthroughs with the same enthusiasm you showed for screen-free victories. The programming skills they're building now, whether in Scratch, Python, or Arduino, create trajectories toward careers that don't exist yet, but the persistence, systematic thinking, and comfort with complex tool mastery transfer everywhere. You're not just teaching code, you're teaching them how to learn hard things.
That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. New episodes come out every Monday, Wednesday, and Friday, so there's always something new to dig into. If this episode was helpful, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It sounds small, but it actually makes a huge difference in helping other parents find the show when they're searching for answers like this. And make sure you hit subscribe or follow so you get notified the second a new episode drops. See you in the next one.